So let's look at an actual question. In this particular case, I have a chlorine gas coming into a carbon rod. And the reason they've had to use an inert carbon rod is that chlorine is not a metal, it's one of our halides, and it's gas form and it won't conduct electricity. So we've had to use carbon to be able to have that conductive electricity. We have our cobalt on the other side. So then I'm going to look at, well, how do I work out which one is the cathode and the anode? So in this case, I'm going to use my standard electrode potentials, and I'm going to look at the fact that I have my chlorine, which is positive 1.36. I haven't got cobalt on this table. So the way I can actually look at it is go, well, let's have a look at something similar to cobalt in terms of the reactivity series. So if we go back up to our reactivity series, and we have cobalt here, and it's above copper, but it's pretty close. It's between nickel and iron. So let's have a look at whether we have iron, nickel. So we have my iron and I have my nickel. So they're both negative. So it's going to be similar in value to these. So our more positive is going to be reduced. So our more positive was definitely the positive 1.36. So in this case, that means then that this is going, my chlorine will have to be my cathode. It's going to be reduced. Okay, so the cathode is positive, which means that our cobalt becomes our negative and is going to be oxidized. Our direction of flow of electrons is always anode to cathode. So we need to put in our direction of flow of electrons. Our salt bridge, because this is negatively charged, our anions move towards the cathode. So our negatively charged anions move towards the anode, and our positively charged anions move towards the cathode. So cations to cathode, anions to anode. So we have ticked off that we have labelled the cathode and the anode. We have done the direction of flow of electrons, and we've done the movement of ions in the salt bridge. Now we can actually calculate the electrode potential or the half cell potential of the cobalt half cell, because we've been given a piece of information and we know that we can use our half cell here. So remember our E cell, electrode potential of our cell is equal to the electrode potential of our cathode minus the electrode potential of our anode. So we can actually work out this electrode potential here by then saying, well, the electrode potential of the anode, which is what we're trying to work out, is going to equal E. I take that over that side, then I need to take this over this side. So it's going to be equal to the cathode minus the electrode potential of the cell. So my cathode electrode potential, we know from here, is positive 1.36, and we were told that this was 1.64. So we're going to take away 1.64. So that will be 40, so that's going to be negative 0.28 volts. So in this way, we can actually then determine what that theoretical value would have been. Okay, so notice in this diagram, even though most of the time you will see the anode on the left, it isn't always the case. So don't just assume, well, the anode's on the left. You need to actually work out which one is going to be reduced. So reduced is our more positive. Our anode is being oxidized, so it's the less positive. So the oxidation is always the more reactive of the two.